Imagine you're trying to classify images. You train a neural network to say whether or not an item is in an image. Is there an animal? Yes. Is there a dog? No. Is there a cat? Yes. Is there a table? Yes. And so on. Maybe you have 1,000 categories of things. What is a cat must be an animal. Tables are furniture. A glass must either contain liquid or not. You don't want to say cat but no animal, or a glass that contains neither liquid nor does not contain liquid. In other words, you want your model to be coherent. You want it to describe situations that can actually happen. One obvious way to get this is just to enforce this stuff on the model's output. Somehow post-process the output to arrive at the nearest coherent state. But at least in theory, you don't have to. If you correctly penalize your model for being wrong, and if it is properly trained, its outputs should always be coherent. In this video, we'll prove the theorem that shows this, but first, we have to talk about loss functions and proper scoring rules. Imagine working on a simpler problem, say telling the difference between an A scribbled on a blackboard and an alpha. That is, we feed the model a bunch of letters on the blackboard, each of which is labeled with whether it is meant to be an A or an alpha, and ask the model to predict these labels. What do we want? We want the right answer to be the one that the model assigns the highest probability to, and beyond that, we don't care. This might lead to a loss function, or a way to quantify how wrong the model is so it can correct itself, that looks like this. As long as the model is right, we don't penalize it, but if it's wrong, we penalize it a lot. While there are many reasons that such a loss function might be bad, one major issue is that the model will not express any degree of uncertainty. If there's a scribble with 60% of mathematicians running it would have meant A, the ideal model should probably not output 90% as its answer, and instead, something like 60% is a better output. But a model trained like this, with our curve as its loss function, will have no reason to do so. It is more or less indifferent to outputting anything between 70 and 100%, and anything less than 70 just leads to the model doing worse on average. Put more concretely, we want to incentivize the model to output the probability that a scribble was meant to be an A or an alpha, as opposed to a number bigger than 50% for an A and less than 50% for an alpha. To do this, we need a proper scoring rule. If the model thinks that a letter is an A with probability P, it should output P. As the model is trained to minimize its penalty, that means that the expected value of its penalty should be minimized when its output is the probability that a given scribble is an A. Mathematically, if X is the output of a model, that looks like this, where S of X and A is the penalty we give to the model if its output is X and the scribble is labeled A, and S of X and alpha is the penalty if its output is X and the scribble was labeled alpha. One example of a proper scoring rule is log loss, which is very commonly used for classification problems. The nice thing about log loss and other proper scoring rules is that they also help incentivize the model to stay coherent. No matter how bizarre the distribution of your input data is, if the model truly minimizes its loss, its output will be coherent. More precisely, given a proper scoring rule and incoherent model output, there is a coherent output that has less loss regardless of the true labels. Note that in the above, we have to choose the coherent output before we see how the data was labeled. But even if the labeling is completely wrong or utterly bizarre, as long as the labeling could mathematically occur, meaning both an event and its opposite don't happen, with the proper scoring rule, the coherent output will be penalized less than the incoherent one. Just to emphasize this, we don't even have to see the data that the bad output came from at all. We just need to know what the incoherent output is to surely do better than it. While the proof of this theorem is by no means profound, it is still worth giving, in part because when applied to the log loss function, it naturally leads to many quantities important in information theory. To start, let's take a quick detour into the land of convex functions. A function f is convex if f evaluated at the weighted average of 2 points is less than or equal to the weighted average of f evaluated at those 2 points. More intuitively, this means that f is curved upwards, or equivalently, is less than or equal to all of its secant line segments. Some useful properties are that the sum of two convex functions is convex, and that if L is a set of linear functions, the function made of the pointwise maximum of all functions in L will be convex. Finally, a convex function always has a unique minimum. All of these statements are not too hard to prove from the definition of convexity, and proving them yourself is a good exercise to make sure you understand. To begin the proof, let S be a proper scoring rule and define phi of x to be this, which is just the expected loss we saw earlier. In the special case of log loss, this is just entropy, roughly the information we gain from seeing the outcome of an event. It turns out that phi will always be convex. This is because, if S is a proper scoring rule, we can write it like so as the maximum of linear functions. But we want to consider all outputs of a model so we can analyze coherence. To do this, if a model gives n outputs, we put them in a vector capital X like this, and we write phi of capital X like this, as the sum of phi of all the little x's. This is the expected total loss of a model's outputs. I will use capital letters to denote vectors and lowercase to denote scalars, but from this point forward, everything is either a function or a vector. Next, from our expected loss function phi, we can define what is called the Wegmann divergence between two sets of probabilities x and y, as the upside-down triangle is just a fancy way to symbolize taking a derivative in multiple dimensions. Honestly, it doesn't really matter, and it's just a way of formally describing exactly what we mean. What the Wegmann divergence really is a quantification of extra loss. I think the world is like y, but it is actually like x. How much extra loss will I incur as compared to if I knew the world state? With this noted, it is natural that Wegmann divergence is greater than or equal to 0, with equality if and only if x equals y, which can be proven from the convexity of phi. When using the log loss function, Wegmann divergence becomes KL divergence, which is a way to quantify how much more surprised you will be with incorrect beliefs than with correct ones. Also, importantly, when regarded as a function of y, Wegmann divergence is convex as the sum of convex functions. Next, consider any possible output x, which we take to be the possibly incoherent output of our model. By convexity, among coherent outputs, there's a unique output C that minimizes the divergence between x and C. Take any coherent output y, which will represent the true state of the world. 1 minus t times c plus t times y is coherent because the space of coherent events is convex. We can find the following. Taking the limit as t goes to 0, using the definition of the derivative, this becomes, which simplifies to in words, this means that if the world is in an arbitrary state y, then guessing c will incur less excess loss than guessing x on average. If we take y to be a certain state of the world, where all events have a probability of either 0 or 1 of happening, we will always incur less excess loss, which is just a rewording of our theorem. Looking back, this means that if we use a proper scoring rule, not only can we interpret our model's output as a probability, but for a well-trained model, its output on the training data will always be coherent. And if the model is not overfit, for any input similar enough to the training data that we can reasonably expect the model to generalize to, the model's output will be coherent. While for a complicated enough set of outputs, it might seem like you need to add additional training steps or complicate your model to obtain a coherent output. This theorem says that to some extent, the model naturally has a worldview that could be the true state of the world.